In this video, we're going to see how to find a state transition matrix, which is phi of t. So here is the phi of t. So phi of t is nothing but e to the power of at, where a is in matrix format. So a value is given -2, 0, 1, -1. So phi of t e to the power of at is nothing but I plus at plus 1 over 2 factorial a square t square plus 1 over 3 factorial a cube t cube plus etc etc. I already showed this in the previous video, so that's the reason I'm just flying through. So here I have I found a square, which is a times a, also found a cube, which is a square times a. Okay, so phi of t equal to I is nothing but identity matrix 1 0 0 1, a is nothing but -2 0 1 -1 times t 1 over 2 factorial a square is nothing but 4 0 -3 1 times t square, and a cube is nothing but -8 0 7 -1 t cube, etc etc. Now what I did here, I took out all the individual terms. So 1 -2t, so t is here, so 2 times -2t plus 1 over 2 factorial, so 4 over 2 factorial, 4 came there, times t square plus -8 over 3 factorial t cube, etc etc. And the second term, every term I have 0 there, so 0 plus 0 plus 0, so I'll end up to 0 there. Here is the third term, fourth term. Now what I did, I converted that into e to the power of -2t. So the first term 0 is there, this is e to the power of -t minus e to the power of -2t, and this is e to the power of -t. Now if you separate this, you will end up with this term. Okay, so this is a little bit hard way. Now I'm going to show you a little bit easy way to find state transition matrix. This is called state transition matrix. State transition matrix. Now I'm going to show you how to find it in S-domain, easy way. Now we know that e to the power of at, Laplace transformation of e to the power of at is 1 over s minus a. Now here a is a scalar quantity, small a is a scalar quantity, so that's the reason we end up with s minus a. If I have a matrix format e to the power of a, then the Laplace domain is nothing but si minus a, where I is the identity matrix. So 1 over si minus a, we can write it as si minus a inverse. So phi of s in S domain, which is state transition matrix in S domain, equal to si minus a inverse. Now if I do the inverse Laplace, I will end up with e to the power of at, which is I will end up with phi of t. So to find the state transition matrix, all I need to do is find si minus a inverse. So I'm using the same A matrix which I used in the previous example. So here I have A equal to -2 0 1 -1. So I'm going to use the same thing, -2 0 1 -1. So si minus A equal to s plus 2 0 -1 s plus 1, that is si minus A. So phi of s is si minus A inverse, whole inverse. So s plus 1 0 1 s plus 2 1 over s plus 1 s plus 2. So phi of s is nothing but I'm going to pull this denominator inside. I will end up with s plus 1 over s plus 1. Usually we don't cancel out, but if I write this down, it will end up, cancel out the pole 0. I can write this as 0 over s plus 1 plus 1 over s plus 2. Now let me leave it like that, then I will show you what happens. Now here this part we need to do the partial fraction. So when you do the partial fraction, I end up with 1 over s plus 1 minus 1 over s plus 2. Here also I can do the same thing. I can write it as 0 over s plus 2 plus 1 over s plus 1. Now when I convert this into time domain, 1 over s plus 2 is nothing but e to the power of minus 2t. So I can say 0 over s plus 1 plus 1 over s plus 2. When we do the inverse Laplace transformation, this is e to the 0 times e to the power of minus t plus e to the power of minus 2t. Since this is 0 times, I'm ignoring that, so that's the reason I just had e to the power of minus 2t. So e to the power of minus 2t, 0. Here 1 over s plus 1 is nothing but e to the power of minus t, minus 1 over s plus 2 is nothing but e to the power of minus 2t, and 1 over s plus 1 is e to the power of minus t. This is phi of t. So this is the easy way to find a state transition matrix. Thank you.